Good morning, everyone. I hope you are ready for our lesson for today. By the way, I am Joan May Emil Yapre, and our topic for today is all about ALU Adder Circuit. Our lesson, let's define what is an ALU. So an ALU is a digital circuit used to perform arithmetic and logic operations. It represents the fundamental building block of the central processing unit or the CPU of a computer. We have four arithmetic operations. These are addition, subtraction, division, and multiplication. We also have seven logic gates, namely NOT, AND, OR, NOR, NAND, NOR, XNOR. Four out of these seven logic gates are considered as the major logic gates. These are the NOT, AND, OR, and the XOR. So I think you have now the questions on your mind about what are logic gates. So logic gates are the switches that turn on or off depending on what the user is doing. They are also the building blocks for how computers work. Aside from that, logic gates turn on when a certain condition is true and off when the condition is false. So for an instance, let's say the switch. So once the switch is on, that means that it is in true condition. While if it is off, that means that it is in false condition. Always remember that true is equal to on and it is also equal to 1, and false is equal to off and it is also equal to 0. Always bear in mind that computer wouldn't take an input of 5 or 6. All of the informations need to be zeros and ones. So reminder, input refers to the information you give the logic gate and output refers to what it spits out. Since we are done defining the ALU, let's now have the adder circuit. So what is an adder circuit? An adder circuit is a digital logic circuit in electronics that implements addition of numbers. These are used to calculate addresses, similar operations, and table indices in the ALU or the arithmetic logic unit, and also in the other parts of the processors. So there are two types of adder circuit. The first is the half adder circuit, and the second one is the full adder circuit. Let's have first the half adder circuit. So, a half adder circuit is defined as a combinational circuit that performs the addition of two bits. And this circuit needs two binary inputs and two binary outputs, which is the sum and carry. The sum is represented by S and the carry is represented by C. This is very useful when you want to add one binary digit quantities. The half adder circuit adds two binary digits called as oggend and addend. The oggend refers to the number to which an addend is added, while the addend refers to a number which is added to another. And as what I've told you, half adder circuit produces two outputs. In half adder circuit, the primary output is only 1 if one of both inputs is 1, but not if both are 1, and that's the sum. The second output is only 1 if both inputs are 1, and that's carry. Let's now have the truth table of a half adder circuit. So as you can see, The sum can be found using the XOR operation and the carry using the AND operation. Given the inputs A and B, we can now get the sum and carry. How? You are just going to add inputs A and B. As what I've told you earlier, the primary output, which is the sum, is only 1 if one of both inputs is 1. But if it is both zeros and ones, the sum is equal to 0. Let's try to add the given inputs A and B. Let's start with the first one. So 0 plus 0, the sum is equal to 0 and the carry is also 0. So for the next one, we have 0 plus 1, the sum is 1 and the carry is also 0. And for the third one, we have 1 plus 0, the sum is 1 and the carry is also 0. But for the last one, we have 1 plus 1, the answer is 1, 0. So 0 is written in the given column, which is the sum, and the carry of 1 over to the next column. So always remember that in binary arithmetic, operation starts from the rightmost side. That is the reason why the 0 is located or found at the sum column, while the 1 is written on the carry column. If we are going to observe the sum here of the inputs A and B for the first given value, which is 0, so it is 0 because both inputs have a value of 0. That is the reason why the sum is 0. And same with the last given value for the inputs A and B, which is 1. It will also give a sum of 0. So for us to better understand how we come up with this one, let's discuss the XOR. So the XOR is the short way to say exclusive OR. Like OR, XOR also needs one input to be on for it to spit out on, but unlike OR, when both inputs are on, XOR spits out off. And it is also off when both inputs are off. So let's proceed now with the second output, which is carry. So as you can see, the carry will only have a value of 1 if both the inputs are 1. But if it is not, carry will have a value of 0. As what I've told you, we use AND operation in getting the carry. So unlike NOT, AND needs two inputs. It only turns on when both inputs are on. If only one input is on, it spits out off. If both inputs are off, then it also spits out off. So with the truth table given, the half-adder logic can be implemented. So the sum or S of inputs A and B here are being implemented using the XOR logic gate, while the carry or C of both inputs A and B is implemented using AND logic gate. So I hope that you're able to follow and understand what half-adder really is and how the sum and carry are being solved. And lastly, how the half-adder is being implemented using the XOR and AND logic gates. Since we are done discussing about the half-adder circuit, let's now have the full adder circuit. So what is a full adder circuit? A full adder circuit is a combinational circuit that performs the addition of 3 bits, where 2 can be referred to as operands and 1 can be referred to as bit carried in, and produces 2-bit output. And this can be referred to as output, carry, and sum. And compared to the half-adder circuit, full adder circuit is difficult to implement. With this full adder truth table, we can say that the sum output is equal to 1 when only one input is equal to 1, or when all three inputs are equal to 1, and the carry output has a carry 1 if 2 or 3 inputs are equal to 1. To get the sum in full adder circuit, we need to add first inputs A and B to get the partial sum. And after that, we are going to add the partial sum into the input carry to get the final sum output. If any of these two half-adder logic produces a carry, there will be an output carry. With a given truth table, the full adder logic can be implemented. The first XOR shows the sum of inputs A and B, and the second XOR gate shows the partial sum together with the input carry to get the final sum output. So based from the truth table, we can say that both the half adder produces a carry, so that means to say that there will be an output carry which is being implemented using the two AND gates. So carry output will be an OR function of the half adder carry outputs. Since we are done discussing about ALU Adder Circuit, we're going to have a quiz. So break a leg and have a nice day, everyone.